So in our last lecture we saw a few reactions, and one of them was the hydrolysis of an ester under acidic conditions. So that's taking an ester and turning that into an alcohol and a carboxylic acid. So the reverse reaction of that is called a Fischer esterification. So in a Fischer esterification reaction, this is one of my favorite reactions from this chapter. It takes a carboxylic acid, and so we're starting off here with the carboxylic acid, and these things, remember, these things smell bad, and we're going to add here an alcohol, right? Now the conditions that we need here are concentrated H+. So usually you'll see that is like conc H2SO4. So in lab you'd put in, depending on your quantity, you'd put in a few drops or a mil of concentrated sulfuric acid. And then what you make is an ester. So ester, these things smell good, they smell great. So it's the common ingredient in flowers and perfumes and odors that are esters. And you get water is one of your products there. So if you can take that last mechanism that we did and write it out kind of in reverse, then that's exactly what we're going to do in this reaction. So let's take a look at the mechanism here. So let's take a generic carboxylic acid here, and let's add sulfuric acid to that. So sulfuric acid is HOOH on the other side, and a bunch of lone pairs there. So remember, we want to protonate the most basic oxygen first. That's the most basic. So we're going to come over here and we're going to grab one of these H's. Okay. So what that's going to make here is your R protonated carbonyl, and then your OH down here. Now, just as before, we're going to have resonance here, so we're going to go through those pretty quickly for the structure. That'll give us this. And then the last one would be this. So our next step will be the addition of the alcohol. So here we'll just add an ROH. So we're going to come around here and we're going to attack this carbon. Right, same reason before, because that's where that plus charge is. And we're going to do this. Okay, so what that's going to give us here is your ROH. Now I'm going to swing around this group right here and place it up above. So we're going to put it here as an OH there. And then that's going to be your OR group with an H. All right, and then lone pairs, positive charge. So basically, here's our strategy. We want to get a neutral compound, and then we want to lose water. So remember, we can't kick off OH minus because we're in an acidic environment. So we're going to go through here, and we're going to deprotonate that OR group here. Now, to do that, we could use a variety of compounds. We could use the alcohol here, or you could use HSO4 minus. So I think your book uses the alcohol, so we'll just stick with that. So that's what we're going to do. So that's going to give us our carbon here with two OHs and an OR. And if you recall from our last lecture, that thing is called an ester hydrate. So we're halfway done right now. So what we're going to do now is we're going to continue this. And again, the idea, our game plan is, it doesn't matter which one of these guys, but we're going to protonate one of these guys. And then we're going to kick it off and be essentially done with our mechanism. So let's come around here. Let's come down and let's grab an H. And we're going to get that H again from sulfuric acid. So if we want to draw that all out again, we can do this. And we're going to swing around here and grab that H. So that'll give us an OH2 plus and your OR group here. Right, now here is our good leaving group. So we're going to kick that off. And when we do that, what we're going to end up getting down here is an R group, carbon, OH, OR, and a plus charge. Now, I don't really mind, by the way, if you were to take a set of electrons and do this for that movement, or a set of electrons and do that for that movement. In the end, we're going to end up with the same 3 resonance structures. Right? So one of our resonance structures is going to be an R, OH, OR plus. So how do we get that? Well, we do this. Okay, and then the last resonance structure that we would get would take these electrons, plop them down, and give that oxygen back. It's 2 electrons, so it has no more formal charge there. So that'll give us our R, C, double bond OH. This is the one we want, because that is just one little hop away from the final product. So we're going to go through here, and to do that, that last deprotonation, let's just use H2SO4, the conjugate base of that, hydrogen sulfate. So let's use that. Let's come around here and grab that H, and then voila. What you get there is you get your sulfuric acid back, so it's catalyzed here. And then now you have your ester. So here is our ester. And that thing smells good. So oil of wintergreen is a common experiment that we'll do in lab. We make isoamyl acetate, which is smells like bananas. It's used as a flavoring agent in like Laffy Taffy and stuff like that. So I want you to start feeling comfortable with kind of going back and forth with this type of a reaction, so that you don't have to just rote memorize mechanisms. So the hydrolysis of the ester and the formation of the ester are related reactions. Now, one little side note about this is that these reactions are equilibrium reactions. So you'll notice that I drew arrows, reversible arrows, as we went through most of those steps up above. So up here we have concentrated H+. Right, here's our generic reaction. And the Ka for this reaction, and you can look these things up in tables, but they're like 3-ish or so, right? They're close to equilibrium, which means that you don't form a lot of them in the course of a reaction. So you have to pay attention to stoichiometry during the course of these reactions, and be careful as you carry them out. Now, what do you do if you want to favor the products? So how do you favor the products? Well, we can do a couple things. We can remove the ester or the water. So we can apply Le Chatelier's principle, right? We can have a large excess of reactants and then do a purification. And then really the easiest thing to do is, if you really want a lot of your ester, is you start off with something like an acid chloride instead of a carboxylic acid. So that third little bullet point there really means don't do the Fischer esterification. Carry out some other type of synthesis. Now in lab we don't typically work with the acid chlorides. They're just a little bit trickier to deal with. They have different safety concerns, so we typically just deal with the carboxylic acid and do a Fischer esterification, and then do cleanups afterwards with liquid extractions and stuff like that. Now, there's other ways here too, other than starting off with acid chlorides, in which we can make carboxylic acids. And that is using a compound called a diazomethane. So this is something that we talked about a little bit in our chapter 19. So these are they're great reactions, but if you look at that first little bullet point, there's a problem. Number one, toxic, right? And azide groups can be explosive too. So it's an explosive compound. So it requires special glassware to deal with. Now, as far as the Lewis structure of this thing, this is what our Lewis structure is. So I've drawn it out here for you. Now, the reaction mechanism here is pretty straightforward to look at. So here is the way we would typically see this reagent, right? So as we go through and look at our mechanism here, we'll see how this thing works. So it's actually pretty straightforward. So I want to point out too, there's one other product that we get. So here we have an ester, and we ought to add in here the other product. And that other product is nitrogen, and that's a gas. But that's a very stable molecule, and the formation of that thing just drives and pulls this reaction over to form the ester here. Okay, so let's take a little look at the mechanism. It's a simple three-step mechanism, just three little processes here. So step number one is we're going to start off here with our carboxylic acid. Right? Now to that we're going to add our diazomethane. Now one thing I want to show you over here as we do this is let's take a look at this and see this actually has an interesting resonance structure. Right, so what we can do is we can take a set of electrons here and we can swing them around and we can do this. And then that would take these and put them here on our carbon. So what that would give us up here is a CH2 minus, and then a nitrogen with 1, 2, 3 bonds down here at the end, and a plus charge right there. Now that right there, folks, is where that nitrogen is going to come from in this reaction. Okay, so down here below, when I write out our diazomethane, I want to write it out as CH2 minus and then N triple bond N. I want to use this form, this resonance form of that. So really the very first thing that's going to happen in that reaction is because you have a carboxylic acid, you have this acidic proton right here, and then you're adding to it the CH2 minus. These cannot cohabitate. So what happens is that very quickly deprotonates this. Okay, so what we form there is an R, C double bond O, O minus. And then we'll just write down here plus resonance. We don't need to draw that out. But the other thing that we get here, right, so that CH2 becomes a CH3. So then that becomes a CH3 N triple bonded N plus. Now remember, we said this thing right here, that's actually going to be a fantastic leaving group. So what happens now is that the negative charge of the carboxylate is going to swing over here, grab this carbon, and then we're going to kick off nitrogen gas. So what we're going to get here is our final product is our R group, our carbonyl, and an OCH3. Right? So there's our ester, and then we also get that nitrogen gas. Remember that arrow up means that you have a gas there. Right? So it's a very convenient mechanism. as far as its simplicity, and it's one of those things that you guys need to make sure you remember. So it pops up in this chapter from time to time.